Alright, so I have a sad story to tell you. I just did 64, and I made a little mistake at the end, and I couldn't figure out what the mistake was. I have figured it out now. So anyway, I have it all done here, so I really am not so inclined to redo the whole video. So what I'm going to do is I'm just going to talk you through what I did here. So in number 64, we have the, this is that steel ball swinging down into this, and it is an elastic collision. When you read that it's an elastic collision, that is a red flag, or flag of whatever color you prefer, that tells you, hey, pay attention, this means that kinetic energy is conserved. That's not generally true in collisions, but it's only true in elastic collisions. So the first thing we need to do in this problem, oh, by the way, this is a really good practice for your ballistic pendulum practicum, although that one is an inelastic collision, which makes things easier. If the two objects stick together, there's only one velocity afterwards, so that's generally easier. If things bounce off each other, then you really need to know this to be able to do much. So anyway, but it's the same principle in the sense that we're going to use energy considerations first, and then figure stuff out with momentum after the collision, before and after the collision. So as this ball swings down here, it has mgh worth of gravitational potential energy, swings down, that turns into kinetic energy, and so we see this v equals square root of 2gh expression yet again. And the velocity of that steel ball is going to be 3.7 meters per second right before the collision. Now, I'm going to set up two different equations here. One for the momentum being conserved, which I'm just going to write in general like that. That's my sort of high concept equation. And then here, this is the mass of the ball times its initial velocity. It's going to be equal to the mass of the ball times its final velocity, which I did v little b, and then plus mass of big B, velocity big B. That's the mass and velocity of this after the collision, because they're both going to be moving. So plug in some stuff here, and then I get this equation which relates VB, I just multiplied it through by 2 here, by the way, to get rid of the 0.5s. And that's an equation that relates VB and V big B. So I need this kinetic energy relationship to be able to do finish the problem, because I have two unknowns here, so I'm going to need two equations. So kinetic energy also conserved, set up the same thing. There's kinetic energy of the ball. That's the only thing moving before the collision. After the collision, they're both moving. So plugged stuff in. I multiplied through by, I canceled the 1/2 before I plugged the stuff in here, just to make things easier. And then I multiplied through by 2 again to get rid of the 0.5s. And then once I got to here, I solved this equation for v little b, and I plugged it in here. I substituted that in here. And then I did some math, and then I got this equation, and then I did some math wrong. This is where I made the mistake. I divided through by VB here, and then divided by 30. So 37 over 30 is 1.23. And then I forgot that I canceled one of those, and I took the square root of it. So that's what I did wrong in the first video. So 1.23 meters per second. And then just like any system of equations problem, bring that over here now, plug that in, and get the velocity of the ball after the collision. And I'll show you that that's all good. So I have 3.7 minus 5 times 1.23. And that's negative 2.45. I guess they had a little bit different rounding scheme going on. Okay, and then if we just wanted to double check, which probably we should here, or I should, because I've been messing up, I could check to see if both of these things are true. So what is the total momentum before the collision? The total momentum before the collision is the mass of the ball times its velocity. The total momentum after the collision is the mass of the ball times its velocity, and the negative sign matters, right? Because momentum is a vector, plus the mass of the block times its velocity after the collision. 1.85. All right, so that's good. And then the same thing should check out with kinetic energy. 1/2 mv squared. That's the total kinetic energy before. And then that should equal the total kinetic energy after, which is 1/2 mass of ball times its final velocity. Now that's negative. Of course, the negative is going to get squared off, but I'll do it like that. 1/2 mv squared plus 1/2 mv squared. And hopefully that is about 3.4. 3.4, 3.4. Why are they not exactly the same? Because of rounding. All right, so that all checks out. There you go. There's number 64.